The sea, once it casts its spell, holds one in its net of wonder forever. Jacques Cousteau. Watch to the end. The most unusual anatomical detail is revealed at the very end. Monognathus ahlstromi belongs to the order Saccharingiformes, a lineage of deep-sea eels that abandoned conventional skeletal symmetry. It inhabits bathypelagic depths, often beyond 1,000 meters, where pressure is extreme and light is absent. At first glance, this eel appears incomplete. Its body is extremely elongated, thread-like, and delicate. The skin is smooth and lacks prominent scales. Fins are minimal. Everything about its morphology suggests radical reduction, except for one structure: the lower jaw. In Monognathus ahlstromi, the lower jaw is dramatically extended forward, while the upper jaw is reduced. This asymmetry gives the species its common association with one-jaw eels. The mandible is not just long, it functions as a forward-projecting capture tool. Unlike fast predators that rely on speed, this eel relies on geometry. The extended lower jaw increases effective strike radius without requiring powerful musculature. In a food-scarce environment, extending reach without increasing metabolic cost is a decisive advantage. Its eyes are small, consistent with life in near-total darkness. Vision here is limited. Bioluminescent cues dominate detection. The body's elongated, flexible structure supports neutral buoyancy and minimal energy drifting. Most deep-sea fish reduce bone density to conserve energy. Monognathus ahlstromi goes further. Ossification is minimal, and skeletal elements are simplified. This reduces weight and allows precise balance in the water column with little muscular effort. Midway through this analysis, recall Darwin's principle. It is not the strongest of the species that survives, nor the most intelligent, but the one most responsive to change. Charles Darwin. Monognathus ahlstromi is not strong. It is responsive. It sacrificed bilateral jaw symmetry, a foundational vertebrate trait, in favor of a specialized feeding adaptation. That is evolutionary risk taken under environmental pressure. Now here is the rarely discussed detail. Embedded within the tissues associated with the lower jaw is a specialized glandular structure believed to produce toxin. Unlike typical venom systems with obvious fangs or grooves, this eel's toxic mechanism is subtle and not externally dramatic. The mandibular extension is not only a reach advantage, it is likely a delivery interface. This biochemical adaptation compensates for limited bite force, allowing immobilization of prey that might otherwise escape. This combination, mechanical extension plus chemical assistance, is not widely emphasized in popular summaries, yet it fundamentally changes how we interpret its feeding ecology. The body remains narrow and low-mass to reduce drag. Locomotion is slow, controlled, and energy-efficient. Vertical orientation while drifting may increase interception probability of small migrating organisms. Reproduction follows the eel pattern of leptosphalus larvae, transparent ribbon-like juveniles that inhabit upper waters before metamorphosing and descending. This dual-phase life cycle connects surface productivity with abyssal specialization. Ecologically, Monognathus ahlstromi occupies a mid-level predatory niche. It consumes small nekton and crustaceans while itself remaining vulnerable to larger deep-sea predators. Even in darkness, trophic structure persists. Its morphology is not grotesque, it is strategic. Reduced skeleton, minimal fins, asymmetric jaw, possible toxin support. Everything unnecessary was removed. Everything useful was exaggerated. If this changed your understanding of deep-sea evolution, support the channel. Like this video, subscribe for precise, research-based ocean analysis. Share it with someone who thinks evolution only works in sunlight, and write in the comments which deep-sea species we should analyze next. Your engagement directly supports more high-accuracy content.